Section 2.2 is talking about polynomial functions with higher degrees. So what we'll look at is using transformations to sketch graphs of polynomial functions, use the leading coefficient test to determine the end behavior of the graphs, find and use zeros of polynomial functions and use those to help us sketch, and then talk about the intermediate value theorem to help locate zeros of the polynomial function. So these first few slides are just a lot of talking points. The idea at this point, we can graph zero functions with 0 degree. Remember, and a 0 degree function would just be a horizontal line. If you have a first degree function, that would be like y equals mx plus b. You would just have an oblique line. And a second degree function is your y equals your ax squared plus bx plus c, which would be your parabola. So polynomial functions that have a degree greater than 2 are a little bit more difficult to sketch, just there's more that goes into them. And so we're going to start looking at symmetry and zeros and just end behaviors for these to help us sketch them. A couple things to remember with polynomial functions is that your polynomial function has to be continuous. So this first graph right here, this is a continuous function right here, right? It doesn't have any breaks in it. Where this graph here is not continuous, you have the break in the graph right here. So B would not be a polynomial because it's not continuous. Another feature of polynomial is it has to have smooth, rounded curves or turns if it changes direction. So now obviously, like if you have a line, a horizontal line, or a first degree polynomial, which would be your oblique line, there's no curves in it and it's not changing directions. And so that's okay, that's a polynomial. But what happens is if you change direction, right, if you have a parabola that has a nice curve, and the more degrees you add, the more potential curves you have. And so here, if you notice when this is changing direction, it just is that nice curve, kind of like a roller coaster. As opposed to like the absolute value function where it's more of that sharp turn. So that would not be a polynomial if you have these corners or these sharp turns in your graph. Those are not polynomials. So this is a little bit what we've talked about. Your polynomial formula right here, remember that you have that leading coefficient and that you have this x to the n, and n has to be greater than or equal to 0, and it has to be an integer. Your simple graphs are your monomials, and then you move from there. So your monomial, going back to this, would be like saying f of x. It just has one term is what the monomial means. So like x squared or f of x equals x cubed. So more of those parent function polynomial graphs. We'll get to kind of back to this slide in a minute when we have more examples. But the idea here, if they talk about a power function, they're really just talking about that polynomial function. So you have it's raised to a power, it's raised to some degree. So in this first example, we have to sketch the graphs of negative x cubed to start. We'll go red. So negative x cubed, remember, crosses at 0, 0. And the difference here is this negative out front. So remember your normal x cubed graph goes like this. So your negative x cubed graph would just go in that opposite direction. For part B, x cubed plus 1, this tells us that we're going to shift everything up 1. So instead of crossing at 0, 0, we'll cross at 0, 1. And then it's that positive leading coefficient, so we're still going to be increasing. And then if we look at this graph, this x minus 1 means that we're going to be going to the right 1. So we're going to shift to the right 1, and then we still have that increasing graph. So the leading coefficient test is really the idea of it tells you what the end behavior or what happens to those arms of your graph. So when we look at the leading coefficient test, if your degree is odd and your leading coefficient is positive, then what happens is that as x goes towards negative infinity, your y value will also go towards negative infinity. And as x goes to positive infinity, your y value goes to positive infinity. So that's when your leading coefficient is positive and your n is odd. So an example could be like a y equals 2x cubed plus 3x plus 1. Right? We have a positive leading coefficient and an odd degree. So again, if we had a negative leading coefficient and an odd degree, something like this. And I don't know that these equations aren't the graph, but it's more of that odd or a negative leading coefficient, odd degree. Then it switches, your arms switch. So when x is going towards negative infinity, your y goes towards positive infinity. And as x goes towards positive infinity, your y goes towards negative infinity. So then when we look at when n is even, so when n is even and a is positive, so your leading coefficient is positive, then both arms will go towards positive infinity. If your leading coefficient is negative, then both arms will go towards negative infinity. So let's use that with this next example to describe the right and left hand behavior. So when they want you to describe that right and left hand behavior, so your right hand behavior, you would describe it as x approaches infinity, because as you're going to the right, your x values are going towards infinity. Where is the y value or the f of x value going? So we have to look, and we have it's an odd degree and it's negative. So remember, the negative odd degree is going to look like that, or some version of that, which means that as x is going towards positive infinity, your y value is going towards negative infinity. Your left-hand behavior would be when x is going towards negative infinity, your y value would be going towards positive infinity. We would be looking at that behavior right there. So the zeros of a polynomial, they could have a function of degree n has at most n real zeros. So if you have a degree 3, you could have at most 3 real zeros. You have at most n minus 1 relative extrema, and an extrema is just a max or min. So if you had a 4th degree polynomial, that would mean that you could have at most 3 maxes and mins. You don't have to have that many, but you could have at most that many. And then we know that a 0 for the function is when y equals 0. So if we were to plug a 0 in for our f of x and solve for our x values, those would give us our zeros. So here's just some vocabulary for you, because sometimes the words the zero, solution, factor, x-intercept, there's a lot of different ways that you're going to have to write them. So if they ask for a 0 is in the form of x equals a. So 0 is an x equals just some value. If they want a solution, that's also an x equals the value. If they ask you to write it as a factor, you have to have it in factor. So you would move the a to the other side and you would have x minus a. And if you want the x-intercept, we write it as a point. So you would say a comma 0. So for this next example, we have to find the zeros, which means we have to plug a 0 in for f of x. So we have x cubed minus x squared minus 2x. We're going to have to factor out the GCF, which is x. We have x squared minus x minus 2. So now we can factor x squared minus x minus 2 into x minus 2, x plus 1. So this is factored form, but it asked us for real zeros. So if we go back to the slide, remember real zeros should be in the x equals some value form. So we have to set each factor equal to 0. So we have 3 factors here. So we would say x equals 0, x minus 2 equals 0, and x plus 1 equals 0. And so now when we solve for x, we get x equals 0, x equals 2, and x equals -1. And those would be the zeros. So you have 3 real zeros, which if you go back, it was a third degree polynomial. So that works with the rules. So if you have repeated zeros of a polynomial, those are said to have a multiplicity of higher than 1. They occur more than once. So an example would be if you had a function, and sometimes when it's in factored form, maybe you have x minus 2 squared times x plus 1 cubed. So the 0 at 2 would have multiplicity 2, and the 0 at -1 would have multiplicity 3. So if k is odd, so in this case, like 3 is odd, then that would mean that the graph would cross at x equals -1. But when your degree of that factor is even, then we would know that it would just touch at x equals 2. So if we were sketching this by hand, first let's find the zeros. So if we plug a 0 in for f of x and we factor out the GCF, which is x cubed, we're left with 3x minus 4. So when we look at these zeros, this has a multiplicity of 3. So x equals 0 is going to have a multiplicity of 3. This factor only has 1, so this would just have a multiplicity of 1. And if we were to solve, we would get x equals 4/3. So what we know that they have odd multiplicities, so they're going to cross the x-axis at both of those points. If we use our leading coefficient, it's positive, right? So we have a positive leading coefficient with an even degree. So what we know then is that the arms of the function will both go towards positive infinity. So if we were trying to sketch this, we would have that it crosses at 0, this is 1 and 2, and 4/3. And so it would probably look, we don't know exactly what happens in between, so you could just draw something where it goes in between and it crosses and those arms go up to the top. Now, if you put it in your calculator, there's probably something else that's going on in there that might be a little bit more squiggly, because since you have a degree of 4, you could have up to 3 maxes and mins, right? So let's put that in our calculator and see how close we were with that sketch. So if you were to graph the graph from the actual calculator, what you find is that we were pretty close, right? It does cross here and here, but what happens is it comes down and it kind of squiggles through and then goes down and comes back up. So without a calculator, this is probably what you would come up with. With a calculator, you'd be able to just be a little bit more precise with it. And then the last idea is the intermediate value theorem. And what the intermediate value theorem says is that if you have some value, some y value here, and then you have another y value up here, that there has to be, because you have a continuous function, that there has to be some y value in between those two y values. So what you would use this for is maybe coming up with where you could find some zeros without actually having to find the zeros. So on this one, we have to find 3 intervals of length 1 where we would be guaranteed to have a 0. So what you're going to want to do is graph this 12x to the third minus 32x squared plus 3x plus 5. And so if we were to graph that, it looks like we're going to cross somewhere in here and here. 1, 2, 3, somewhere here. and up here. So we have a graph that kind of looks like this. Should be what your calculator looks like. So 3 intervals of length 1. So what we know now is we have a 0 right here. So if we were writing an interval of length 1 for that, we would just say that there is a 0 between -1 and 0, right? Since to the left of the 0, your graph is negative, and to the right of your 0, it's positive. So that intermediate value theorem says that it has to pass through 0 to get from the negative number to the positive number. There's also a 0 between 0 and 1. For that same reason, we change from positive to negative. And then there's a 0 between 2 and 3, since the graph is changing from negative to positive, and it's continuous. Your graph would have to pass through that 0 to get to that point.